And this is part 2 of section 5.3 examples. So here we're proving by mathematical induction another inequality. We missed question 4 last time. So we have that want to prove that for any bigger than 5, 2 to the n is bigger than n squared. As always, we want to prove the basis case, which in this case, because we start at 5, we're going to try with p of 5, which will be 2 to the 5, which is 32, is bigger than 5 squared, which is 25. So we're good. Now, assume that for k that belongs to the integers, you have p of k, where p of k holds. This means that 2 to the k is bigger than k squared. So now, this is step 2. Now we want to show, step 3, that 2 to the k plus 1 is bigger than k plus 1 squared. So step number 4, let's prove it. We start with 2 to the k plus 1. And because we want to put this in terms of the p of k condition, then we're going to see this as 2 times 2 to the k. Now, 2 to the k is bigger than k squared by hypothesis of induction, right? So this is bigger than twice k squared. But now, 2k squared is actually going to be bigger than k plus 1 squared. And so this will prove what we want. And then p of n is going to be true for all n bigger than 5. This is by principle of mathematical induction. Oh, wait, but why this is true? We didn't prove this part, right? So let's actually check it out. So notice that, or we actually mentioned something similar to this before. We have that k squared, well, we can see this as k squared plus 2k plus 1, right? So this is essentially, I'm saying that 2k squared is bigger than this. So what I'm essentially saying is that k squared is going to be bigger than 2k plus 1, or that k squared minus 2k minus 1 is bigger than 0. We actually proved this in another proof in the past. This is just saying that k times k minus 2 minus 1 is bigger than 0. But remember, because we have that k is bigger than 5, then this is going to be k times k minus 2 is actually going to be bigger than 5 times 3, which is 15. So k minus 2 minus 1 is actually bigger than 14. And so because it's 14 is bigger than 0, and then we can go backwards from here, and then that's going to turn out that this is bigger than this, and so this happens. So the reason why is because something that we have proved before showed this inequality. But otherwise, you can just prove it again doing this step. Okay. Now let's go for question 6. So this is let's prove by mathematical induction that 3 to the n is bigger than 1 plus 2 to the n. So now, of course, this is for n bigger than 1. So we're going to prove the p of 1 step. Notice that 3 to the 1 is actually bigger than 1 plus 2. Wait a minute. This is not okay. Okay, so something is not okay here because we cannot say that 3 is bigger than 3. So let's correct this. Let's see if this works for n equals 2. So let's replace here p of 2. 3 squared is actually bigger than 1 plus 2 to the 2. This is 9, and this is 5. Okay, so for 2, this is true. So we're going to need to fix this and replace this by 2. This is just an example to show that if my initial condition doesn't work, it might work for the next one, but we might want to be careful when you're proving the basic condition. Now, for some k, we're going to assume that p of k is true. So this means that 3 to the k is bigger than 1 plus 2 to the k. And this is what we call our induction hypothesis. This is our step 2. This is step 1, step 2. Step number 3 is to state what we want to show. So we want to show that 3 to the k plus 1 is bigger than 1 plus 2 to the k plus 1. And step number 4 is prove it. So we start by 3 to the k plus 1. We can see this as 3 times 3 to the k. And of course, we apply by hypothesis of induction. This is going to be bigger than 3 times 1 plus 2 to the k. Okay? Notice that I apply the hypothesis of induction when I assume that 3 to the k is bigger than 1 plus 2 to the k. Now, let's work with this inequality. Notice that this is essentially 3 plus 3 times 2 to the k. But we can just see simply this as 3 plus 2 to the k plus twice 2 to the k. 3 times 2 to the k can be split between 2 and 1, right? So now this is 2 to the k plus 1. So notice we're getting, this is something that we can separate as 1 plus 2 to the k plus 1. We get a 1 from here, and we get the 2 to the k plus 1 from here. And then we have plus something else, which is 2 to the k. So this is actually bigger, by definition, than 1 plus 2 to the k plus 1. So we're good. This proves my k plus 1 step. And so by principle of mathematical induction, P of n is true for n bigger or equals than 2. Okay? All right, so now let's go to question 7. So for question 7 here, we're proving that for n bigger than 1, 1 plus x to the n is bigger than 1 plus nx when real numbers are bigger than minus 1. So first, the basic step, right? Step number 1. We proved by the condition in P of 1. We have that 1 plus x is bigger or equal than 1 plus x. So in this case, it works because it's bigger or equal. So we got it. Now, assume, step number 2, assume that for k that belongs to the integers, 1 plus x to the k is bigger than 1 plus kx. This is our induction hypothesis or hypothesis of induction, right? So now we need to show, or we want to show, that 1 plus x k plus 1 is bigger than 1 plus k plus 1 x. That's what we want to show. Now, step number 4, show it or prove it. So we start by doing 1 plus x to the k plus 1. And so, of course, as you will probably think by now, I'm just going to separate this as 1 plus x times 1 plus x to the k. Since we already have the hypothesis of induction, we're going to use that. And this is going to be bigger than this. So this is going to be bigger than 1 plus x times 1 plus kx. This piece goes in here by hypothesis of induction. But now if I multiply that, then this is being bigger than 1 plus kx plus x plus kx squared. But now I can just get something together. This is equals to 1 plus k plus 1 x plus kx squared. But notice, this is the term that we wanted. And this is actually something larger because we have some extra stuff. So this is clearly going to be bigger or equal than 1 plus k plus 1 x. So we're done in what we wanted to prove. So 5, by principle of mathematical induction, we have that P of n is true for all n bigger than 1. And of course, in this case, x bigger than minus 1, because that's a condition of our particular problem. Now, question 9, the last question that we have over here. Wait a minute. Now we have question 8. We want to find the smallest integer that n factorial is bigger than 3 to the n. And we want to show for mathematical induction that that's going to work out for n bigger than n0. So notice that here we don't know the initial condition, so we gotta look for the initial condition. If I do n equals 1, I get 1 factorial, which is equals 1. This is less than 3, so this doesn't work. If I do n equals 2, then I get 2 factorial, which is equals 2. This is less than 9, which is 3 to the n, so this is not going to work out. N equals 3, then 3 factorial, which is 6, which is less than 27, so it's also not going to work. So let's keep going. N equals 4. 4 factorial is now 24. And this is not going to be less than 81. So boom, I keep going. N equals 5. 5 factorial. Now 5 factorial is 120. And this is not going to be less than 243. This is not going to be bigger than 243. So it doesn't work. So I'm starting to think that maybe it's not true. Let's see. N equals 6. 6 factorial. 6 factorial is now 720. And this is yet less than 729. But ooh, look at this. Starting to catch up. So 3 to the 6, which is 729, still bigger than that. Now for n equals 7, 7 factorial is actually 5,040. And this is going to be bigger now that 2,187, which is 3 to the 7. So we found our number. So this is true. N factorial is bigger than 3n if n is bigger than 7. Okay? So this is our step 1. This is the basic step. So now I want to prove that this is going to be true for something larger than the bigger step. So let k belongs to the integers, k bigger than 7, of course, because we're assuming that got to be bigger than the base case. So the p of k is that k factorial is bigger than 3 to the k. And we want to show, and this is our step, this is step number 1, step number 2, step number 3. We want to show that k plus 1 factorial is bigger to the 3 to the k plus 1. So let's prove it. Start at number 4. So let's prove it. K plus 1 factorial is just going to be k plus 1 times k factorial. But by hypothesis of induction, we have that k factorial is bigger than 3 to the k. So we have that this is bigger. This is going to be bigger than k plus 1, 3 to the k. Okay, by induction hypothesis. Or by hypothesis of induction. Now, at this point, notice that because k is bigger than 7, so in particular, that means that k plus 1 is going to be bigger than 8, which is going to be bigger than 3. So this means that k plus 1 factorial is bigger than k plus 1, 3 to the k, which is bigger than 3 times 3 to the k, and so that's bigger than 3 to the k plus 1. So we just proved that k plus 1 factorial was bigger than 3 to the k plus 1, and we just show what we wanted. So P of n is true for n bigger than 7 by principle of mathematical induction. All right, so now let's move to number 9, which is really the last term. So in here we have a sequence here, and we want to show that the multiplication of those numbers are going to always be less than the square root of 1 over 2n plus 1. So first, the basis step. So step number 1. Let's prove for n equals 1. So p of 1. So for p of 1, this is saying 1 is going to be less than. So for n equals this, the first term here is going to be, if I plug in 1, I get 2 minus 1 over 2, so 1/2. So notice that I'm doing the multiplication from 1 up to this point. So this means that it's going to be 1/2 on this is the left side. And now the right side is plugging in here. I'm going to get 2 plus, so less than 1 over square root of 3. And this is actually true because the square root of 3 is around 0.577. So it's a little bit more than 0.5. So this works. Now, for the step number 2, assume for k that belongs to the integers with k bigger than 1, that you have 1 1/2 times 3/4 times 5/6 times 2k minus 1 over 2k is less than 1 over 2k plus 1. Okay? So this is our p of k. So now number 3, I want to show that p of k plus 1 holds. So I want to show that 1/2 times 3/4 times 5/6 times 2k minus 1 over 2k times 2k plus 1 minus 1 over 2k plus 1 is still less than 2 square root of 2k plus 1 plus 1. Okay? So big play of inequalities in here. So now number 4, let's show it. And so, of course, we want to start with one of the two sides. We're going to start with the left side because it's easier. So we'll start with 1/2 times 3/4 times 5/6 times 2k minus 1 over 2k. And so this is pretty much the first part. And this is the piece that is given by the k plus 1 step. And let's actually simplify this. So this is 2k plus 2 minus 1. So that's going to be 2k plus 1. And in the bottom is going to be 2k plus 2. Okay, and by hypothesis of induction, this is going to be less than this one is less than square root of 2k plus 1. So 1 over 2k plus 1 times 2k plus 1 over 2k plus 2. So, and by the way, notice that this that I want to prove is just 1 over square root of 2k plus 3. That's what I want to prove. Now, I have this one here so far, but notice that this is just equals to 2k plus 1 over just 2k plus 2, the square root of 2k plus 1. And if I just cancel out this term with this term, I'm just going to end up with the square root on the top, 2k plus 1 over 2k plus 2. And now, what I need to just show this is what I have so far, and I want to show now that this is less than 1 over 2k plus 3. Okay, this is going to be this, and so at this point I conclude my proof. By principle of mathematical induction, we have that P of n is true for n bigger than 1. But let's showcase that this is actually true. So I'm stating here to conclude the proof that this is true. But let me show you that this is true. Turns out that, so this part, imagine that you have a square root of 2k plus 1, and you multiply by 2k plus 3. So we're doing it backwards. So this needs to be less than 2k plus 2. But this is just the root of 2k plus 1 times 2k plus 3 less than 2k plus 2. And this is just to show that this is true. Notice that this now I'm going to multiply by the same inequality twice. So now I'm going to get 2k plus 1 times 2k plus 3 less than 2k plus 2 a square, because we multiply the inequality by itself. And so now what we're going to get is that 4x squared plus 8k plus 3 is less than 4k squared plus 8k plus 4. This is what I get from this. This is what I get from this. Notice that I can cancel term, and I'm going to get that 3 is less than 4. So this means that this inequality is true. I can start now going backwards on my argument. I can see 3 is less than 4. So this is less than this. And so this is less than this. And so I go backwards, get roots on this side, I get this. And from this one, I can get this one. Okay? So that will be my way to show it. So this exercise in particular is quite difficult because it has very complicated inequalities, but it's just an example of the type of thing that you can show with the principle of mathematical induction. Okay, so this concludes what we do with the principle of mathematical induction in terms of divisibility and inequalities.